This is Dr. Muhammad, and this is the seventh video in this series in analysis of statically indeterminate structures. And I'm going to talk today about part 3 of the method of consistent deformation, part 3. And I'm going to talk about internal forces and moments as redundants. So actually this is the main topic for today's video. We are going to talk about the internal forces instead of external forces. Before, in the previous videos, we used the external forces as redundant. But here we are going to talk internal forces or moments, whatever, as redundants. Okay? So this is the major difference between this video and the previous videos regarding the method of consistent deformation. Let's have an introduction to whatever or what we are going to do for today. So we have analyzed externally indeterminate structure with a single degree of indeterminacy by selecting support. Take care here, the word support. Support, it means what? Something like external support reaction, okay, as the redundant. The analysis of such structures can also be carried out by choosing an internal force or moment as the redundant. So this is what I'm talking, or this is what I have already explained in the previous slide of the title, that we are going to focus on internal forces. So it is going to be like we can use it instead of using the support reaction or the external force, provided that the removal of the corresponding internal restraint from the indeterminate structure results in primary structure that is exactly determinate and stable, the two main conditions that always we should maintain. So we know this very well, that we want these two conditions to be maintained if we are going to use an internal force or moment as our redundant. Okay, it is similar to the case of the external force as redundant. Okay, let's consider this beam that we have. Let's consider the two-span continuous beam shown here. As you can see, it is continuous span. We are going to solve it to get an idea and to have an understanding of the method using this simple two-span continuous beam. As you can see, we have AB loaded with two concentrated loads, 10K or 10 kips, and we have the span BC loaded with 12K at distance 10 feet from the point C. If you look here, first we are going to look to the number of unknowns for this system. We have hinge at A, which means that we have two unknowns here. We have roller at B, means that one unknown, and we have another roller at C, which is another one, another unknown. So we have 1, 2, 3, 4 unknowns, and we have only 3 equilibrium equations. This means that our system, this two spans continuous beam, is once statically indeterminate. Okay, once statically indeterminate. Okay, actually from this system we can look and we can say it is once statically indeterminate. We can simply remove one of the vertical reactions. We can remove, for example, this restraint or this restraint, any one of them, and then we're going to render our system to be determinate and stable as well, right? So, but whenever we talk about continuous beams, especially for unequal spans, okay, especially for unequal spans, it is more convenient to select any internal bending moment as redundant, like the moment at B, okay, the moment at B. So this is commonly or a kind of more convenient procedure or way for the solution of the two spans, especially unequal spans, continuous beams. Okay? Okay, so let's consider that the moment that is going to be developed at point B, okay, at the interior support B, let's consider it as our redundant. It is going to be our redundant. Okay. First, we need to notice something here, which is that at point B, even that the structure is loaded and the elastic line is shown dashed here, the dashed line is representing the elastic line of this continuous beam, you're going to find that the slope at point B is continuous. Continuous means that there is no abrupt change in the slope before and after B. It is smooth, okay? So this is what we call it the tangent at point B, and you are going to find that the elastic line is smoothly changing. It is something, if we say something like this, so the elastic line is making something like this. It is smooth. And here the tangent, which is this one, is considered to be representing the slope at this particular point. Okay? Okay. So this is what we said here, that the slope of the elastic curve of the indeterminate beam is continuous at B. This is the first notice that we should take care of. Okay. Now let's go to the second level. When the restraint corresponding to the redundant bending moment MB is removed, let's assume that we are going to remove the restraint here. Let's assume that there is no continuity in the slope here. We are going to introduce an internal hinge. This means that there is no continuity at point B, and the slope before and after point B is going to be different. We are going to indicate the slope before point B as theta BL, which means left, and on the right it is going to be, the slope is going to be theta BR, which indicating the right slope. And both of them, theta BL plus theta BR, both of them are going to give or make what we call it theta BO, or node relative. Relative means that the relative slope or angle between the tangent before B, I mean that the tangent before, I mean that on the left of point B, and the tangent on the right of point B, based on the elastic line or the new elastic line after the introduction of the internal hinge. Okay? Okay. So, if MB is removed by inserting an internal hinge at B, as shown, a discontinuity develops in the slope of the elastic curve at B. As we can see, we have discontinuity, in the sense that the tangent to the elastic curve at just the left of B rotates relative to the tangent at just to the right of B. As you can see here, this is the tangent before, this is the tangent after. Both of them, they are going to have this value or this theta. So we are going to say that theta at point B, due to the original load and relative between the left and right, is going to equal theta before the point B, which is theta at the left of point B, plus theta at the right of point B. This is what we want up till now. Okay, so now remember that our indeterminate beam, the slope of the elastic line was smooth, but when we introduced the internal hinge, we found that the slope is going to be discontinuous. Okay? Okay. Now let's go to the next part and see what we are going to do. Remember that our indeterminate beam is going to be, we are claiming that our indeterminate beam is going to be the superposition of two systems. One system is related to the primary beam subjected to external loading, which is the loading that already we have, plus the primary beam, means that the same internal hinge introduced here, loaded with 1 unit moment working in the same sense or the same direction of the moment MB at point B. Okay, so we are going to say that our indeterminate system is going to be the superposition of the two of them. Let's see more about this and understand what is the meaning of this. When we removed the moment MB from here and we introduced the internal hinge, there was this theta BO relative, right? This means that the redundant bending moment MB provides continuity of the slope, because when we removed MB from here, we found that there is discontinuity. So based on this, MB provides continuity of the slope of the elastic curve at B in the actual indeterminate beam. It must be sufficient, it must be of sufficient magnitude to remove the discontinuity, which is this one. This is the theta, or the angle of discontinuity. Okay? So this MB must have a sufficient magnitude to remove this discontinuity from the primary beam by bringing the tangents back together, right? This is the point. This is the key point. Okay? So in this case, we are going to claim that removal of F of MB from here and only letting the external load being applied, then if we add to this system the same primary system but loaded with the redundant, which is MB, the redundant is going to be loaded by adding unit moment at point B and multiply it by the redundant, and multiply it by the redundant. Okay, so this is the case for us. This is the superposition of the two systems now. Okay, the beam, let's go one step ahead. We want to put two things here to understand before going into the next step. We need to know that the beam convention is that redundant MB is considered to be positive. This is a kind of, we call it the beam convention, okay? The sign convention for the moment. It's considered to be positive when it causes compression in the upper fibers and tension in the lower fibers of the beam. Okay, remember that well? This is what we call it the beam convention. Positive when compression in the upper fibers and vice versa applies. When we apply this kind of internal unit moment, an internal bending moment is defined by a pair of equal but opposite couples. Okay, pair of equal but opposite couples. So they are going to work like this. Okay, so something like this. This is, we call them pair of equal, means that the magnitude of both of them is equal, okay, but opposite, they are having different sense. This is clockwise and this is counterclockwise. Okay, this is clockwise and this is counterclockwise. Okay, and then due to the application of this type of moment here, we are going to find that there is theta at point B, because unit moment at point B from the left, and we are going to have another kind of theta, which is, we call it F here. F, it is the flexibility coefficient. Okay, so flexibility coefficient means that it is the theta, or the angle. Now it is the angle. Before it was deflection, here it is the angle. We call it the flexibility coefficient. So whenever that we add this unit moment here, it would cause an angle to take place or to occur, and it is going to be B, means that the slope at point B, due to application of unit moment at the same point B, due to or on the right of point B. Okay, and FB, B relative, it is going to be the summation of both. If you look here, this is the tangent before, this is the tangent after, this is on the left, this is on the right. Both of them, they are going to be added together to give us FBB relative. Okay, so it is going to be FBB relative. Okay, now let's go to the next step. Well, where is the compatibility equation that we are searching for, or we need to go and start to apply? Our compatibility equation, remember that we said that our structure is one statically indeterminate. So we need only one additional equation to make our structure determinate. So we are bringing now the compatibility equation, the additional equation, to the equilibrium equations in order to make our system to be determinate. And in this equation, we are going to put it as we have done before in the previous videos. We're going to say that theta BO relative, which means that the angle or the rotation at point B due to the original loading plus the rotation due to applied unit moment at point B times the redundant MB, which is the moment at point B, equal to 0. Why it is equal to 0? Because we said before that our system, remember that our system, it was elastic. In the indeterminate, it was elastic. The curve was elastic. Means that the deflection or the slope was smoothly, the slope here is the same. Before and after, the slope is the same. But the slope is the same means that the relative or the difference in the slope is going to be 0. This means that due to external loading, rotation, plus the rotation that is going to be applied due to our redundant, both of them, they are going to cancel one another. And we are going to end up with slope that is going to be smooth, or tangent, or a slope that is going to be smooth in the elastic line. Okay, this is the meaning of the compatibility equation here. Pretty similar. It is pretty similar to what we have explained before regarding deflection, but instead of deflections, we are dealing with rotations. Okay, so since each of the spans of the primary beam can be treated as a simply supported beam, the slopes at the ends of the left and right spans can be easily computed by using conjugate beam method or deflection formulas. Now the question that is going to come up in our minds is how we can get this slope and how we can get this slope. This equation, which is the compatibility equation, we know that our main unknown is MB. But this deflection due to the external loading and this rotation due to the external loading and this rotation due to unit moment applied, we do not know them, but we want to get them as we have obtained the deflections before regarding the deflection or the vertical deflection. Then the answer is we are going to have two ways for obtaining these rotations. We can use way number one, which is conjugate beam method, or way number two, which is deflection formulas that already you have an idea about it before. Okay, so we have two methods here based on which we can obtain the rotation due to external load and unit moment at point B. Okay, now let's go and see this. How we can obtain the rotation using the conjugate method. So we are going to draw our system, okay, after introducing the internal hinge at point B. So we are going to have like simple beam on the left and on the right of point B, and the conjugate beams for the external loading are shown as you can see. Recall that the slope at a point on a real beam is equal to the shear at the point on the corresponding conjugate beam. In the conjugate beam, we are loading it with what we call it the elastic moment. Elastic moment. I'm sure that you know well what I'm talking about because this is something that you have studied before in structure analysis 1. So whenever that we use conjugate beam, we load the beam or we load the span with elastic moment which is the value of the real moment divided by the inertia, which is EI, and we are putting it on the span. As you can see here, the arrows are heading up, and whenever that we are going to calculate the reactions and the shear of this conjugate beam, the shear of the conjugate beam equals to the slope of the real beam. Okay, I know that you know this very well. If you are not familiar with this or you forgot about it, you can revisit it in the textbook, or you can revisit your notes for structure analysis 1. Okay, so here we need to make the conjugate beam. It's very easy. We have 10 and 10K for the span AB. We can draw the moment. It is very easy for us to draw the moment. It is going to be something like this, which is already written here. It's 60 and 60 over EI. And for this span, we have 12 concentrated load at distance 10 from C and 20 from B. Then we're going to have 80 over EI, which is the moment here, and the arrows are heading up. The reactions at the supports of this conjugate beam is heading down. Okay, it is heading down or going down, as you can see here. Okay, its direction is down. Okay, well, how we can obtain the slope now? So we are here at this point, at point B. So for member AB, the reaction is 420. 420, it is the shear, which means that it is the slope, 420 over EI. And it is counterclockwise, counterclockwise. So whenever the shear, as you can see, it is from the right and heading down, it is counterclockwise. And the opposite applies if it is negative. So it is going to be clockwise. What is the sign convention for such kind of a thing? Where I can find it? You can find it in the next slide. This is the next slide. So the positive, if we are talking about if the positive ordinates of the M over I, which is the elastic moment, okay, diagram, are applied to the conjugate beam as upward loads, okay, in the positive Y direction and vice versa, then a positive shear in the conjugate beam denotes a positive counterclockwise slope of the real beam with respect to the undeformed axis of the real beam. And what is the positive here? The positive, if this is the span, if this is the span of the beam, if the shear is from the left and going up, then it is positive. Or it is from the right, looking from the right and going down, it is positive. And vice versa here. If the span like this and from the left it goes down, the shear is going down, then it is negative shear. And if it's from the right and going up, it is negative shear. Going back to our case, here at B, it is 420 and going down. So here, from the right and going down, so it is positive shear. Positive. So we are having positive here, and positive means counterclockwise. Counterclockwise, as we said here. Counterclockwise. So we are okay now. Okay, now let's go to the beam BC. The shear is going down from the left. Going down from the left. This means what? Negative. Negative shear. Negative shear means it is negative. Negative means what? Yes, clockwise. It is clockwise, as you can see here. Okay, at the end, we said that the total relative slope or relative angle at point B is going to be theta B left plus theta B right. So we have 420 from here and 533 from here. Okay, left and right. Then we are going to end up with this, which is 953 for theta B node relative. Okay. Okay. Now for the conjugate beam, remember that we were talking here about what? The conjugate beam for external loading. So the loading here is, this is the external loading. Okay. Now let's go for, exactly, for value, unit value of the redundant MB. So we are talking about conjugate beam for unit value of the redundant. So here in the unit value, we are not doing anything, just we have what? One unit moment applied here and here at point B. Two opposite with the same magnitude of one moments. As you can, I put it here in red arrows here. And it is the tail of the arrow is up, making tension on the top fibers. So we are dealing with this type of moment. Whenever that we make conjugate beam for this is the conjugate beam here. So we have one unit, one here. So this means that we are dealing with 1 over EI. And on the left, it would be a triangle elastic moment. And here it is another triangle elastic moment. And the value of the base of the triangles is the same here. And they have different heights. So this is going to be F. F means flexibility coefficient, or the rotation at point B due to unit moment at the same point B from the left, which is this one. Talking about this from the left. I'm talking about this moment like this, okay? So when we look to this, what is the elastic reaction here? This is the elastic reaction. Take care the arrows of the elastic moment that is indicating like it is going up, as you can see. So the reactions of each beam should be going down. This means that for our case, this is going down 6.67 from the right and going down. It is exactly, it is supposed to be positive, and the positive means exactly it is going to be counterclockwise. Going here, this is the elastic reaction of this shape, a triangle loaded with or having the base of 1 over EI, and another base, it is the distance BC. Then we can get the reaction, which is 10 over EI. Then this is for beam BC, it is from the left going down, from the left and going down. This means what? Exactly, it is as if it is negative here. So this means, yes, I can remove this negative and put it as, exactly, it is clockwise here. Then FBB relative is going to be FBBL, this one, plus this one. So this is the total summation, or this is the summation, and we are going to end up with 16.67. Okay, now we have the main two deflections, or sorry, the main two rotations of the compatibility equation. Now let's go to the compatibility equation. And remember, this is theta B node relative plus FBB relative times MB. So we have now this FBB, already we have calculated previous slide, and this is we have calculated it 2 slides before. Then the only unknown is going to be MP. One equation, MB, one equation and one unknown, then we can obtain MB as minus 57. What is the meaning of minus here? The negative means compression in bottom fibers and tension on top fibers. This is the sign convention for moments. This is the sign convention for moments. Take care of this. Okay. Now, let's go to the final step, which is how to draw the bending moment, or how to get the shear of the reactions of other supports in our indeterminate beam. First of all, here this is minus 57, and we said that it means compression in bottom and tension on the top fibers. So let's go here. I'm going to put 57. I'm going to divide my indeterminate beam to 3 parts, as you can see. One part, which is the B, where the support is, and this is the left span AB, and this is the right span BC. And I'm going to put the 57 on the 2 beams, as you can see. Top is tension, bottom is compression. So I'm going to make it here on this beam. It is like this. Okay, this is the top tension, bottom compression. Similar here, it is top tension, bottom compression. So I'm going to make it, yes, like here also. This is the case. And then I'm going to put it with the opposite side on the beam here on the point B, which is going to be, as you can see, the same, the opposite of the moment here. The opposite sense is going to be applied on B, and the opposite sense is going to be applied here, and they are having the same moment. This is the main redundant that we have obtained, and we have put it right in our beam now. Okay? We have put it right. So remember that it is as if our beams here and here, we don't have anything except that we have moment here. Okay, and we do not have anything here except that we have moment here. Okay, and this is the value of 57.19 here, and similar value here, 57, okay, 0.19. Okay, then it is very easy. We have external loading. We have external loading here, right? Let's use another color. So the external loading, we have 12, which is being applied here. This is 12. And then we need to know what is the reaction here and what is the reaction here. Taking the moment here, okay, taking the moment, we can easily get the value of the reaction at C. So we can get the reaction here. Seemingly taking the moment here, we have 57 counterclockwise, 12 times this distance is going to make it clockwise, and then the difference is going to be CY, which is given here. Okay, so now we obtain CY. Similarly, we can obtain BY from the summation of Y. Okay, summation of Y equal to 0. We can get BY, and this is due to or from BC. So we put it here BC. Apply the same on this beam. You are going to find that we have only the beam loaded with a moment. Then we have here 2 concentrated loads. They are external loads, 10 and 10, right? Then simply we can obtain the reaction at A, which is AY, and it is going to be 7.4. So we know this value now. And then we can obtain from the summation of Y equal to 0, we can obtain the vertical reaction at B, which is going to be 12.86. And this is what we call it BY from AB, from this span. After that, we have now BY, okay, here from AB, and here it is from BC. So the reaction is going to be the summation of the two, 5.9791 from the right and 12.86 from the left. Then BY is going to be exactly the summation of the two, the summation of the two. Okay, so now this is everything for us, and by solving this is the member end forces and support reactions for the indeterminate beam. This is the final step for us. Maybe I would ask you to make the bending moment and shearing force diagram. It's very easy now for you to make the bending moment and shear force diagram. Okay, very easy for you to make these value. Everything is clear for you. Okay. Now, bending moment diagram, we can make it by simple beam parts. By simple beam parts. So we just putting the external loading moment, which is already we have explained before, 60 and 60, and this is here 80 due to the external loading. Okay, this is due to the external loading, which is due to, yes, here, this is 10 and 10. This means that we are having here, as we have like 60 and 60, and here we have another moment, which is due to this 12. This is the moment due to external loading. We put it here, here, and here. And then we put the moment due to internal redundant that we have put. It is 57.19. It is pretty simple, and it is for the all beam. So it is 57.19 in both, because it's the same at B. If you go back, it is here and here. They are the same. Okay, and they are, as you can see, they are the same magnitude here. And then we just put them together here, just adding them and superimposing them together. Okay, you can leave it like this. I would accept it in this form, no problem. Okay, so this is what we call it, the simple beam parts. Okay, now this concludes the meaning or the way of making the redundant to be an internal force, an internal moment, and we used the conjugate beam method in order to obtain the deflection. Now let's go to see an example, and in this example we are going to use, instead of the conjugate beam method to obtain the rotations, we are going to use the deflection formulas that already we know, or already we have it in our textbook in the front cover, and we are going to use this alternative for the calculation of the rotation. Okay, now this is our example. As you can see, we have here two spans. They are equal spans. We have like 10 and 10, and we have distributed load 15 all over the spans, 60 kilonewton concentrated load at the middle for the span BD. We have something at C, concentrated load. E and I, the inertia, are given to us, and in the same time we are having like 1, 2, because it's hinge, 1, 2, 3, 4 unknowns. This means that we have once statically indeterminate structure. Okay, then I ask you here in this example that take the interior support B to be the redundant, the moment or the bending moment at the interior support B here to be the moment, to be the redundant. Okay, so we are going to remove this roller support and we are going to introduce a hinge here, and we're going to use it as our primary system. Okay, now let's go and jump into the next case. Exactly, we have now the primary beam, which is going to be by introduction or introducing an internal hinge in the middle, and this system is going to be loaded with the external loading, 15 here, 15 and 60, and here this is plus the same primary system loaded with 1 unit moment at the same sense of the assumed redundant, which is going to be MB. So we have, this is the moment sense, okay, clockwise here and counterclockwise in this direction, and it is multiplied by our redundant, our main unknown. This is what we do not know it. Okay, so here this is the primary beam loaded with redundant MB. Okay, unit moment here multiplied by the redundant. Okay, now our compatibility equation, as usual, I think that you are familiar with it now. Theta B node relative, which is all the theta here, that is the difference between the slope before B and the slope after B. So it is going to be theta B node relative plus FBB relative, which is going to be this value, the slope before B plus the slope after B due to unit load, unit moment applied at point B, multiplied by MB, multiplied by this moment. Okay, simply we are going to look to how we can obtain this theta and how we can obtain this flexibility coefficient. This, the first one, due to original loading, it's very easy. We can use it. We can obtain theta BL and theta BR, but we are going to use exactly the deflection formulas. So by using the deflection formulas, we obtain, take care, we want to obtain theta BL and theta BR. We have left and we have right deflection. The first span is AB. It is simply supported span and it is loaded with 15 kilonewton per meter. So it is going to be similar to this case. Look to this case here. This is the deflection formula that you are going to find in the back cover of the textbook. Simply supported, loaded with distributed load. And theta A and theta B can be calculated by our formulas. You can find it here. This is our formula. Okay, theta A and theta B, it is going to be WL cubed over 24 EI, and we have a minus here. Minus means that it is going to be, if we're talking about A, it is clockwise, as you can see. This is the meaning of minus. And theta B, if it's going in this direction, means that it is counterclockwise. So take care of the sign convention here. Minus and positive. Okay, so let's go back. In our case, only one, WL cubed over 24 EI. WL cubed, we are talking about this case. So as if here, so this is AB, so we're talking about this slope, which is like theta B here, exactly. So we're talking about this theta B here, which is going to be positive for us. W, the load intensity, times L cubed over 24 EI. Let's go back. W, which is 15, our load intensity, times 10 to the power 3, which is the span, over 24 EI. This is from the formula. You can obtain theta BL easily. For theta BR, let's have a look here. This is theta BR. It is for the span BD, but this span is loaded with distributed load and concentrated load. So we need to make superposition. Two cases for distributed load and one case for concentrated load. This is why you are going to find here we have the summation. We have one term plus another term. This term due to distributed load. It is pretty similar to the above one, which is 1510 cubed over 24 EI. I here is 2I because this span is double the inertia of AB. Plus, this is the formula for concentrated load, which we can obtain it also from here. This is the deflection formula. This is a concentrated load in the middle, and these are the theta A and theta B. Our case is going to be similar to theta A. So this is our case, minus PL squared over 16 EI. Go back. So it is going to be, as you can see here, 60, which is the concentrated load. Sorry, we're talking about the theta BR here. So it is similar to, if we are going to this case, we're talking about theta. Yes, it is theta, as if we're talking about theta A. Theta A is minus PL squared over 16 EI. So it is, yes, 60, which is the concentrated load, times 10, which is L to the power 2 over 16 over E to I. Okay, so here remember well that we are dealing with the superposition. Okay, so this means that the value of the minus here, the value of the minus here, it is okay, but we want the magnitude actually, because here we are going to say that theta B original is going to be the magnitude of theta B lift plus the magnitude of theta BR. So regardless of the sign, we are going to sum them up. Okay, so no problem here, just we want the magnitude itself. 60 times L squared over 16E times the inertia. We can obtain it easily now. Okay, so now we can get theta BO by summing up these two values here. We are going to end up with 1,125 kilonewton meter squared over EI. Now let's go to the second part, which is we want, yes, the FBB relative, which is the second term in the compatibility equation. How we can obtain it? This is our span, or this is our continuous beam, primary beam, loaded with the redundant, which is only 1 unit moment applied here. So we want to know what are the slope before and after. So we have two spans, AB, which is concentrated moment at the right end. Here we have AB, and we have concentrated moment with the same sense, if you see. So we are interested in theta A, which is theta A here, minus ML over 3E I. So it is, as you can see here, this is 1. There is 1 here multiplied by 10 because we have 1 unit load. So it is already not written, times L. This is L over 3EI, then you can get the value. And for the right, it is going to be similar, the similar formula, but using 2I instead of 1I here. We are going to end up with FBB relative, the summation of the two, this value and this value. We're going to end up with 5M over EI. Okay, 5M over EI. Okay. Okay, now let's go to exactly to the compatibility equation. Our compatibility equation is going to be theta BO relative plus FBB relative times MB, our unknown, main unknown here. So theta B relative already given, and FBB already we have obtained it before. Then MB is going to be the only unknown here in this equation. We can get MB equals to minus 22 or 225 kilonewton meter. This is our main target. This is what we are searching for from the beginning. Okay. Now we can easily go through the remaining part. As usual, we are going to put the minus 22 or 225. We're going to put it here in the beam. So you're going to find it here. Here, 225. It is going to be at the top. Here is tension, and here it is going to be 225. Also, it is going to be tension from the top, because as we said, this is negative moment. Negative moment means that it makes tension on the top fibers and compression on the bottom fibers. So you can put 225 here and 225 here, and then you have a simply supported span on the left and another simply supported span on the right. You can easily get all the reactions, okay? Simply by structure analysis 1, you can obtain everything here. Okay, these are the member end forces and support reactions for the indeterminate beam. Okay, and then you can draw the bending moment using the simple parts, simple beam parts, and then you can end up with this. You can do it by yourself, and you need to get some exercises on this. Okay, but I'm going to leave it for you to do it by yourself. Now let's go to the in-class assignment. So I'm going to give you now an in-class assignment. So you can look to this problem and understand it well, and then stop the video at this moment and try to solve this problem using the consistent deformations method and use the deflection formula, the deflections formula in the front cover of the textbook. Okay, you can use it. This is our system. Okay, so stop the video now and try to solve by yourself and check the results with what I'm going to show it to you shortly. Okay. Now the solution of this equation, as you can see here, we have 50K have middle span, and there is no other loading. It's only concentrated load, which would make our life much easier when we are going to calculate the slopes of the the slopes for the beams AC and CE. We know the E and I, then everything is going to be very easy for us. I'm going to give you the hint. This is the solution of this problem. Okay, so we are going to introduce our internal hinge at point C, and we are going to apply the external loads 50 and 50, and the primary beam is going to be also loaded with 1K foot at point C, as you can see, with a pair of moments applied here. Then we are going to calculate theta at point C left and theta at point C right. We can use the beam deflection formulas, okay? And you're going to find that theta C right equal to theta C left, and please check this value, which is 1800 K foot squared over EI, and you are going to find that the theta C O relative is going to be the summation of both of them, which is 300 or 3600. And for the F, the flexibility FCCL and FCCR, this is the flexibility due to this one, due to the application of unit load. You're going to find it equal to 8 feet over EI. Please check it again, and they are going to be the same from the left and right. Then we have 16. Then for the compatibility equation, you can get the redundant MC, and it would equal minus 22 or minus 225. Please check it by yourself and do it. Okay, I hope that you have obtained this. This is the in-class assignment. If you have any mistake or something, you can repeat it again until that you got the right understanding for it. I'm going to end up with the home assignment. This is a home assignment for you. Please solve it using the consistent deformation method, and you can use the internal moment at B as your redundant. EI, it is a constant, and there is no values here. It is only L and L. So you are going to use these variables, okay? L, and you have distributed load, which is W. Okay, I hope the best for you, and I hope that by the end of this video, you have an idea about internal forces and moments as redundants, and I hope that you could go through the in-class assignment and the home assignment easily without any problem. Okay, thank you, and see you in the next video.